Alright, hello everybody. Um, Hope everything's going alright so far. You're oriented with the course, what the expectations are, where to find everything, where to find resources, how to post homeworks. And hopefully you've made it and found your way to this video. This is going to be the first video. It's kind of excited, so starting off with the first section in Chapter 1. Oops. Again, the way I'm going to run these videos is I will be going through some sort of handout, which is just kind of an outline for me that contains definitions, theorems if they're needed, as well as examples to go through of particular types. And again, I just wanted to mention that, you know, the book that we're using is a first course in differential equations with modeling applications. We're going to mainly be studying what are called ordinary differential equations, and this is where there's only a single independent variable involved, so you can do differential equations with multivariable functions, which not really going to be what we're going to be focusing on here. This PDF can be found, this is a free PDF of the textbook that I found online. Make sure, it might be the case that, when you first open the PDF, it's a seemingly scrolling page by page, but there is a table of contents tab that can bring you to any section in the book. So today we're going to talk basically just about section 1.1, definitions and terminology. The handout that I will be using with the definitions, theorems, and examples that I'm going to go through, that will be posted along with this video it's going to be posted as a Mathematica file, so hopefully you have the ability to download. You're probably going to want to make sure that you download Mathematica. You can find the directions for how to do that at wwcc.edu/mathematica. And there will be times where I might have you submit your homework via Mathematica file. So you're going to want to make sure that you have Mathematica to open the handouts if you want, and to finish homework assignments from time to time. Okay, so let's get into this. So essentially what this course is all about is having equations, basically, well, I guess let me start over. What this course is all about is, say you don't know a function, okay, so a function of a single variable, and say you don't necessarily know that function or any of its derivatives, okay, but you do, say, have some sort of relationship between the original function and its derivatives. Okay, so you don't really know the derivatives themselves, but you know how they're related through some equation or expression. Okay, well, that equation or expression that relates the derivatives in the original function is called a differential equation. Okay, so we're going to talk about differential equations, types, order, and linearity. Okay, so there's different kinds of linear equations. Linear equations have what are called order, and there's also what is called a linear differential equation, and we're going to see many different kinds of differential equations throughout the course. And what we're ultimately going to be interested in is solving these differential equations, so trying to figure out what function, okay, is related by itself and its derivatives in the differential equation that we're given. Okay, so we're trying to basically find solutions that are themselves functions, but we always usually start with a differential equation. So some equation involving a function and its derivatives where they are unknown. Now, the definition of a differential equation, if you're reading up top, okay, is An equation containing the derivatives of one or more dependent variables with respect to one or more independent variables. Okay, so any equation that's containing those or relating the derivatives of one or more independent variables to one or more independent variables is said to be a differential equation, which I will just be calling them DEs. If the equation contains only one independent variable, it is said to be an ordinary differential equation. Okay, so we're basically going to only be working with a single independent and a single dependent variable. Okay, so there's what's called partial differential equations where there's only one dependent variable and there's more than two or more independent variables. Those are called partial. There you would be studying what are called partial differential equations. We're not going to do much of that, if any of that, this quarter. We're going to mainly be studying ODEs. Okay, so only a single independent variable. And then you have an equation relating unknown derivatives, and then of course so basically this equation is going to, or this expression is going to involve the independent variable and the dependent variable in its derivatives. Okay. The order of a differential equation is the order of the highest derivative in the equation. So you might have like a y prime or a y double, like a differential equation with the highest derivative appearing being y prime. Okay, the first derivative would be an order 1 differential equation. If you had y triple prime appearing and that was the highest order derivative, that would be the order of the differential equation. In that case, it would be 3. Okay, so we're going to be studying ODEs. Okay, single dependent variable, single independent variable. Okay, the order of a DE is the highest derivative that appears. The general form of a differential equation, now there's two of them. I guess there's the general form and what is called the normal form. So basically the general form of an nth order differential equation in one dependent variable is basically just obtaining a zero on one side. So say you had some equation, non-zero on both sides. If you would move all the terms from one side to the other to obtain a zero on the right, what you would be left with on the left side would be some function of x, y, and its derivatives. Okay, so there'd be x's in the expression, and then you'd have a bunch of y's and y primes. Okay, so getting a zero on one side is called the general form. Then you have what's called the normal form. The normal form of an nth order differential equation in one dependent variable. Okay, this is where you just essentially solve for the highest order derivative. Okay, so like if your differential equation had at most a y triple prime, you would solve for y triple prime in terms of x, y, y prime, and y double prime. Okay, so this is just, there's two forms. One is get a zero on one side. That's the general form. The other form is solve for the highest order derivative, and then the other side will be a function of the previous derivatives, the original function, and x. We'll see some examples shortly. Okay, so those are the two different forms. Okay, we're going to study the type of differential equation we're going to study are the ordinary differential equations, and then one special differential equation that we're going to look at is what's called a linear differential equation. So an nth order differential equation in one independent variable is said to be linear if it can be written in the form. Okay, so this is the general form. Let me just point this out. Let's look at it term by term. So this would be the term that has the highest order derivative appearing. So again, the dny over dx, that could be like your y triple prime. And it's just saying that you should have a term that has y triple prime, and the a sub n x, that's just a coefficient function. Okay, so you'd have some function of x times y triple prime, and then it just decreases in order. Okay, the next term might be some function of x times y double prime. And you do this until you get down to, now the last term should just be a multiple of y. So So basically it's just saying the left side is, okay, some function of x times y, some function of x times the first derivative, all the way up to some function of x times the highest order derivative. And then on the right side would be some function of x that's left over. So that's all the stuff that does not contain any y's or y primes. Okay, so example 1, if I want to basically classify these differential equations, I want to find the normal form, the general form, and the order, and I also want to determine whether or not these differential equations are linear. Okay. Okay, so for the first differential equation, I'll find the normal form and general form first. So the normal form is just the form that you would obtain by solving for the highest order derivative. So I solve for the second derivative of u in terms of s by subtracting 2s du ds and u from both sides. Okay, so that would be normal form. Or you'll also see me do this from time to time because I think it's more shorthand, it's easier to write. If it's clear that s is the independent variable and u is the derivative in terms of s. You could also write this as u double prime equals sine of s plus u minus 2s u prime minus u. So notice that you're writing the highest order derivative as a function of the independent variable s, the dependent variable u, and the previous derivatives, which in this case would just be u prime. Okay, or the general form, I believe that's the form where you obtain a 0 on one side. So you could just subtract the sine s plus u to the left-hand side. That would give you the general form, and that'd be the Leibniz, actually, sorry. Yeah, that'd be the Leibniz notation, so where you're doing d squared u over ds squared, that'd be the second derivative of u. Or again, you can write everything in the prime notation, which sometimes it's convenient to use one notation over the other, and you'll see when we solve specific types of differential equations. And so notice that the dependent variable u that appears, you don't know that. Okay, you don't know what u is as a function of s. The goal is to figure out what function u is. So a differential equation, again, is just some equation in terms of the independent variable, in this case s, the dependent variable, in this case u, and then possibly its derivatives, okay, in this case u prime and u double prime. So these would both be, okay, so that was the first thing, finding general form and normal form. These would then be what order? Well, the highest derivative that appears is the second, so this is a second, I gotta work on my handwriting with this stylus pen. This is a second order differential equation. Okay, and I also have to determine whether or not it's linear. Okay, so you have to go back to the previous slide. Okay, if I want to determine if it's, I guess, and one thing I want to do is I'm going to rephrase this. I want to say whether it's a linear second order DE or a non-linear second order DE. Now, what I want you to probably look at is maybe the original differential equation itself. Okay, so for this to be linear, okay, out front you would need some function of s, which in this case is the constant function 1, times the second derivative. Okay, so the first term is linear. The second term is some function of s times the first derivative, okay, so it's linear, plus u, which is again a function of s times the dependent variable u. So notice that the dependent variable and its derivatives are appearing in each term, and the coefficient functions are only in terms of s. But the problem is, Okay, so the left side is okay. Right, it's some function of s times the derivative, plus some function of s times the first derivative, plus some function of s times u. Okay, that's exactly what you want. The right-hand side, though, the sine of s plus u, okay, for this to be a linear differential equation, the right-hand side has to strictly be a function of s. So this is not a function of s, or in general not a function of the independent variable. So what we can say is this is a non-linear second order differential equation. And hold on, I must fix one thing real quick. Switch all this to blue. Okay, so again, this term is not a function of s. So in this case, it's a non-linear second order differential equation. Okay? So we got normal form, general form, the order, and we knew how to determine it was linear or not. Okay, now for part B. Okay, so I want to write this in normal form, and I'll just leave it in the prime notation. So in normal form, let's see, I'd probably need to make sure that the only thing that appears on the right-hand side is... I guess I'd have to solve for the highest order derivative. Okay, so first thing I'm going to do, to put this into normal form, I got to solve for the highest order derivative. So the first thing I'm going to do is, I'll probably just solve for y triple prime, and that is equal to, okay, so I'd have to subtract everything from that first term. Okay, so subtract everything off from this and then divide by x squared. So let's see, I would have e to the 2x over x squared times y prime minus y double prime. Okay, and then I'd have plus, oh, that should be a negative. Okay, so sorry, first I had to subtract everything over. This should be a minus, and then I'd have 2xy over x squared, and then finally it'd just be a plus 4 over x squared. Okay. Now that is technically in normal form because I did solve for the highest order derivative in terms of x, y, y prime, and y double prime. And I probably should have put 4 over x squared out front and subtracted those other two terms off. Now if I want to put this in general form, I really just need to get a 0 on one side. So that would be x squared y triple prime plus e to the 2x y prime minus y double prime plus 2xy minus 4 equals 0. Okay, so general form is obtain a 0 on one side, normal form is solve for the highest order derivative, and then depending on what we're going to do, like the normal form up there, I could probably rearrange the right hand side depending on what I was going to do with it. It would depend on how I'm going to solve the differential equation. And again, the goal is to figure out what the function y is when you have a relationship between x, y, and the derivatives of y. Okay. Okay, so we've talked about we've seen a couple examples of differential equations. We've we know what normal form is. We know what general form is, and we also know how to find the order. I guess I forgot to do that in the previous problem. Part B, that was order 3, and that actually was a linear differential equation. Sorry, I was kind of spacey. Let me actually write that out. So the reason it's linear is, and it's order 3 because y triple prime is the highest derivative that appears, but you could write this as x squared y triple prime, and then minus e to the 2x y double prime, plus e to the 2x y prime, plus 2xy equals 4. And what I want you to notice is, okay, each derivative appears in the dependent variable y. If you look out front, each coefficient is a function of the independent variable, and okay, so in the function 4, the constant function 4 is a function of x. So this is a third order linear differential equation. Sorry. Okay, so I forgot to do that. So moving on, we can start talking about what a solution is, what a solution looks like. Okay. So we're going to talk about a couple different things. We're going to talk about implicit solutions of differential equations, and we're going to talk about explicit solutions. You might recall talking about you might remember of how to take derivatives of implicit functions by implicit differentiation, and then just the normal derivative of an explicit function. Okay, the same thing is going to be similar here. So, we'll talk about this in the next part, but an explicit solution is just finding the dependent variable as a function of the independent variable explicitly. Okay, so it'd just be like, f of x equals 3x plus 2. That's an explicit function. Whereas, like, equations of circles are implicit. Those would be implicit solutions because you can't necessarily solve for y in terms of x without restricting the x values. Okay, so any real valued function phi, and it has to be defined on an interval I, that has to possess if it's an nth order differential equation, there needs to be at least n derivatives that are continuous on that same interval I. And if you substitute this function into that nth order differential equation, reduces the equation to an identity, that function is said to be a solution, in particular an explicit solution of the equation on the interval. So that function has to be defined on the interval as well as all of its derivatives. They must be continuous on that interval, and they have to reduce the differential equation to an identity when you solve it and its derivatives in. The interval I is called, well, there's basically way too many things. It's called the interval of definition, the interval of existence, the interval of validity, the interval of the solution, or the domain of the solution. Okay, however you want to phrase that. Okay, example 2 says to verify that y equals 1 over 4 minus x is a solution of the differential equation y prime equals 2x squared. Sorry, y prime equals 2xy squared. Give at least 2 different intervals of definition. Okay. So, what we're going to do is, I'm going to basically look at this function first. So this is supposed to be a solution of the differential equation. Okay, 1 over 4x squared. Now, we know that the domain of this, this is not the interval of... Okay, so the function 1 over 4 minus x squared, this is supposed to be a solution of that differential equation. And the domain, not the same as the interval of solution just yet, but the domain of this function is what? The x cannot be 2 or negative 2. So you'd have negative infinity to minus 2, union minus 2 to 2, union 2 to infinity. Okay. Now, I can look at y prime, which is going to be, however you want to do this, you can use the quotient rule, you can rewrite it with negative exponents and use the chain rule, however you want to do this, but I believe the derivative would be low d high minus high d low over low squared. I believe it ends up being 2x over 4 minus x squared squared. Okay. If you take the bottom function times the derivative of the top, you get 0, minus the top function times the derivative of the bottom, well, minus a negative 2x is positive 2x, and then you divide by the bottom function squared. And you're going to notice that this has the same domain. Okay. Now, the only rule is that the original function and all of the derivatives involved in the differential equation, as well as the, you have to look at the differential equation itself. Notice it's 2xy squared, so there's no restrictions on x there. You need to make sure that the differential equation is defined on the interval, and then the dependent variable and its derivatives need to also be defined and be continuous on whatever interval you choose. Okay, so basically there's only 3 intervals that you could choose for which the interval of solution would be defined. Okay, you have 3 choices. To make them as large as possible, you could choose that as your interval of solution. You could choose this as your interval of solution, or you could choose that as your interval of solution. I'll call this I1, I2, and I3. Okay, so you will notice that the differential equation is defined on those intervals, and y and y prime are continuous on each of those separate intervals. Okay, so any two of those, so any one of those, I'm supposed to give at least 2 different intervals of definition, intervals of solution, domain of the solution, whatever terminology you want to use. But again, the differential equation has to be defined on those intervals, okay, for x. These are the x intervals. And the dependent variable and its derivatives need to be continuous on whatever interval you choose. Okay. And right, the discontinuity is at negative 2 and 2. So any interval that does not contain negative 2 or 2 will be an acceptable interval of solution, unless you require, you might have what are called boundary conditions or initial conditions that force you to be within one of these intervals. Now, if I want to verify it's a solution, what I have to do is, well, again, I might as well write the derivative. What did we have? We had, it was 2x over 4 minus x squared squared. Okay, that's on the one hand. And so I can plug that into the left-hand side now. So if I take this differential equation, the left-hand side becomes 2x over 4 minus x squared squared. The right-hand side is 2x times basically y squared, 1 over 4 minus x squared. And it's basically, remember, it says that a function is a solution if when it and its derivatives are substituted into the differential equation, you get an identity. And no surprise here that the left-hand side, again, is just 2x over 4 minus x squared squared. But when you simplify the right-hand side, that becomes also 2x over 4 minus x squared squared. Checks out. Okay. So, first of all, this is a solution, and I, the domain of the solution, for instance, I could choose -2 to 2, or I could choose -infinity to -2, okay? Or you could choose 2 to infinity. So you have 3 choices for the interval, and generally you choose that interval to be as large as possible. And again, the rule is whatever interval you choose, the differential equation must be defined on that interval, and the y and its derivatives must be continuous on that interval, continuous and defined. Okay. Moving on. How to get through 5 examples. So here's example 3. I'm trying to do this in under an hour. So that was an explicit solution. Again, notice the solution was defined, y was defined explicitly as a function of x. Okay, so now, definition. What's the difference between an explicit and implicit solution? So a solution in which the dependent variable is expressed solely in terms of the independent variable, such as the previous example, and constants, that is called an explicit solution. A relation, again, notice now it might not necessarily be a solution function. A relation g of xy equals 0 is said to be an implicit solution of an ODE on an interval I, provided there exists at least one function phi that satisfies the given relation as well as the differential equation on I. So basically it says it's an implicit solution if there's a way to use it to find at least one explicit solution that also satisfies the relation and the differential equation. Okay, so for instance, example 3, I want to verify that this circle centered at the origin of radius 3, essentially. Okay, that is an implicit solution to the ODE dy dx equals minus x over y. Okay, we'll see in later sections, this is what's called I believe this is what's called an autonomous differential equation, where you'll notice that the first derivative depends on only x and y, or maybe well, scratch what I'm saying. Okay, but the differential equation, this one just involves the first derivative. So basically, what I'm trying to get at here is if x squared plus y squared equals 9 is the solution curve. Okay, dy dx then is just the slope of the tangent line at any point on that curve. Okay, it says find 2 explicit solutions as well as the domain of the solution for each. Okay, so first of all I want to do a verification. Okay. Alright, so to verify, well, notice if you had an explicit solution in the previous problem, you took a derivative explicitly. If you actually want to verify an implicit solution, you can just use implicit differentiation. And again, you're treating x as the independent variable. So, well, the derivative of x squared is 2x plus the derivative of y squared using the chain rule is 2y dy dx, and the derivative of the right hand side is 0. And you'll notice if you solve for dy dx, you're basically subtracting 2x and dividing by 2y, and you get minus x over y. Check. So this means x squared plus y squared equals 9 is an implicit solution of the differential equation dy dx equals minus x over y. Okay. So that was a first order differential equation. Okay. Now, that's just verifying that's an implicit solution. now what I need to do is I need to find two explicit solutions as well as the domain of the solution for each. So basically, if I look at x squared plus y squared equals 9, okay, what that's going to give me is, I can actually solve for y, and this is going to be me giving my two explicit solutions. One is going to be the square root of 9 minus x squared, and the other one's going to be minus the square root of 9 minus x squared, and what you're going to notice is you're essentially just getting what? The bottom half of a circle and the top half of a circle. Okay? Right, x squared plus y squared equals 9 is a circle at the origin of radius 3, because 9 is 3 squared. You can solve for y. Okay, eventually you're going to square root both sides and get a plus or minus. Okay, the plus is giving you the top half of the circle, so that would be one solution curve. And the bottom half is going to be the other solution curve. Okay, so the second explicit solution. And some people might call these y1 and y2. So y1 might be, y sub 1 might be the top half, y sub 2 might be the bottom half. Well, I have to give you an interval of solution, whether I'm using the first one or the second one. Now it's going to be the same in both cases. Now, let's see. Does the interval need to be open or closed? Well, I think I generally like to use the open intervals, but in either case, both these functions are only defined from minus 3 to 3. Okay. And actually, the reason that I know you cannot include minus 3 or 3 is because if you take the derivative of either of these functions, you're going to have a 9 minus x squared in the denominator, and the derivatives need to be defined on the interval of solution. Okay, so very important, right? The derivative of 9 minus x squared, the square root of 9 minus x squared, is negative 2x divided by the square root of 9 minus x squared. That's not defined at 3 or negative 3. Okay, so the intervals of solution are the open intervals because the derivatives need to be defined and continuous on those intervals. Okay, so that was just the solution curve as a piecewise. Again, you have to pick one, and sometimes it's going to depend on initial conditions. You might be given a function value of your solution curve that's either on the top half or bottom half of the circle. Okay, so depending on some other conditions, your solution curve is one of these two, the top or bottom half of the circle. Okay, and again, just notice the differential all a differential equation is a relationship between derivatives and rates of change. Okay. Okay. Now, those were the previous examples were about verifying particular. Those are what I would call particular solutions. The solution functions did not involve any constants. But oftentimes, if you're given a differential equation and you're looking for a solution, you're going to oftentimes end up with a family of solutions. Okay, and depending on which function in that family you would choose for your particular solution is going to depend on some initial conditions, which we may or may not see here today. So, definitions: a solution phi is often referred to as an integral of the equation, and its graph is called an integral curve. Okay. Because again, if you're thinking of a first order differential equation like dy dx, right? The original function is the integral. Okay, so you can think of the solution as an integral, and the graph is called the integral curve. And then second bullet, when solving a first-order differential equation, that would be in the general form, you usually obtain a solution containing a single arbitrary constant or parameter c. The solution then implicitly has the form g of x, y, c equals 0. So that'd be the implicit form. It'd be some function involving x, y, c, x, y, and c. Okay. That is called a one-parameter family of solutions. So a first-order differential equation only has a one-parameter family of solutions. Okay. All right, you can think of it this way. When you find the first antiderivative, okay, usually there's a constant of integration. Right? If you had to further find a second integral, right, there would be a new constant of integration. Okay, so a second order differential equation would be a two-parameter family of solutions. When solving an nth order differential equation, you're actually seeking an n-parameter family of solutions. So some implicit solution would involve x, the independent variable, y, the dependent variable, and then n constants, because it's an nth order differential equation. A solution of a DE that is free of arbitrary parameters is called a particular solution. And sometimes a DE possesses solutions that are not a member of the family of solutions. Such an extra solution is called a singular solution. Okay, so you might be looking for solutions and you find some family of solutions. Okay, that isn't necessarily going to give you all possible solutions. There might be extra solutions called singular. Okay, so just back to this idea, example 4, we'll talk more about families of solutions and particular solutions eventually in later sections. Now example 4, again this is just another verify, except for instead of verifying a particular solution, this is going to be verifying a family of functions as a solution to a DE. We're going to see this model show up later. This is actually a differential equation that arises from a population model. We're going to assume an appropriate interval I of solution. So this is just a solution where the differential equation, well, first of all, notice the differential equation doesn't even depend on t. That's defined everywhere. And then depending on your constant, if you look at p and its derivative, the interval of solution would have to be an interval for which p and its derivatives are continuous. That's going to depend on the constant c. So we're not going to worry about that here. We're just going to assume an appropriate interval I of solution. Now, if we want to verify this, I basically just have to show that, so this is an explicit solution. So I'm going to substitute p and its derivative into the differential equation and see if it reduces to an identity. So first of all, dp dt. Okay, so this isn't going to be as fun, but I have to use the product rule. It's going to be low d high, so it's going to be the bottom function times the derivative of the top, minus the top function times the derivative of the bottom, which is also ce to the t, divide by 1 plus ce to the t squared. Okay, so I have applied the quotient rule. Make sure you review that. Let's see what that simplifies to. I think you're going to get a c squared e to the 2t twice. I believe the numerator just becomes ce to the t, and the denominator will be 1 plus ce to the t squared. Okay. Sorry, that's p prime. So that's actually the left-hand side of the differential equation. I can do a left-hand and right-hand side verification as well. Right? If I look at p times 1 minus p, that's going to be ce to the t over 1 plus ce to the t times 1 minus that. Okay. And I've kind of haven't really left much room here, but if I get a common denominator, okay, turns out that this whole thing right here just equals 1 over 1 plus c e to the t. Okay. So if you get a common denominator, that's what the part inside of the parentheses is. If you multiply that by p, okay, I think you can see that you're just going to get dp dt. Okay, so make sure you verify that. Okay. Or another thing I could do is I could probably just do that slower again. Right, p prime, which is the same as dp dt. Again, we did the quotient rule. And what did I get? I think I just got c e to the t over 1 plus c e to the t squared. Now, that's the left-hand side of this differential equation. Now let's look at the right-hand side again. P times 1 minus p. That's c e to the t over 1 plus c e to the t times 1 minus that. And like I said, if you get a common denominator inside the parentheses, you are going to see that that's just going to end up being 1 over 1 plus c e to the t. Sure enough, when you multiply across, okay, and what that tells me then is, okay, so since I took p and its derivatives, plugged it into the original differential equation, and I got the same thing on both sides, where I got an identity. That means p equals c e to the t over 1 plus c e to the t is a family of solutions to the differential equation above. Okay. Okay. And again, if you were given an implicit solution, you would just use implicit differentiation and simplify it into the differential equation to verify. Okay, but you could get an implicit family of solutions as well. Okay, so last thing is finding a piecewise defined solution to a differential equation. Okay, and then the last part here is constructing a piecewise defined solution of a differential equation. Now, I want to talk a little bit about, again, we're going to talk in later sections about how to solve differential equations and find families of solutions involving constants, arbitrary constants, right? Each different set of constants gives you a different particular solution. I want to talk about, so different choices of C give you different particular solutions. Okay. So for instance, in this case, this is my one parameter family of solutions, so y equals x squared, and then the interval of solution, it and its derivatives are all defined for all real numbers as well as the differential equation. That would be the largest interval of solution. That's a particular solution using, so that's a particular solution with c equaling positive 1. Sorry, again, the pen's okay, so yeah, that's a particular solution when c equals 1. Okay, right, you could choose another one. So that y equals x squared, that's a parabola opening upward from the origin, right? Another particular solution would be minus x squared on the same interval. Again, make sure you verify that the family of solutions to the DE, make sure that y equals cx squared satisfies the differential equation xy prime minus 2y equals 0. So for that one, you could just you could find y prime, and then substitute y and y prime into the left side of that differential equation, if you can show that it equals 0, it is a solution, in this case family of solutions. And then again, I'm not going to write it down because I'm lazy here, but another particular solution would be y equals minus x squared. Again, an interval of solution would be all real numbers. And that's a particular solution that I obtain when c equals -1. Now, if I look at both those integral curves, so right, those solutions were called integrals. You have two different integral curves. You have the one I chose, you have the y equals x squared when I chose c to equal 1. And then you had y equals negative x squared, that was when c equals -1. Those are two different particular solutions, okay, by choosing different values of c. Okay. They both solve the differential equation, but what I'm going to do is I'm actually going to do some cutting and pasting. I could actually, and this is really interesting, you can create new solutions. Actually, there's a couple of them I could create. Notice I could piece together parts of different, I can actually take pieces of different solutions and glue them together. Right, I could take these two pieces and glue them together to get this solution curve or integral curve, which is what I'm actually going to do. That's going to give me my piecewise defined solution to the dE. Right, it's going to be x squared on that part and minus x squared on that part. The other thing I could do is I could take the parts of the solutions that are in quadrants 2 and 4, and I could create this piecewise defined solution where that's x squared and that's minus x squared. So basically, if I go with this one over here, if I kind of cut and paste those pieces of the solution curves for part of, right, I'm taking part of the solution I got when c was 1 and part of the solution I got when c was -1. I'm going to glue them together so I obtain a single well-defined function, and in this case my integral solution, my integral, or my my solution to the differential equation is going to be a piecewise function that's minus x squared when x is less than 0, and it's x squared when x is greater than or equal to 0. Now, you don't need to verify this is a solution if you've verified the family was a solution, because you should already know that x squared and minus x squared satisfy the differential equation. This would be a particular solution, okay, defined piecewise, and it would still have the same interval of solution. Okay, so that's an interval where the differential equation's defined and y and its derivatives are continuous on that interval. And again, I could do that similarly for the pieces that were in quadrants 2 and 4. So this is a way to take your family of solutions, look at two particular solutions in that family, and if I can kind of just pick any pieces that I want to and glue them together in a piecewise fashion to obtain, more, I guess, nuanced, maybe more obscure solutions to my differential equation. Okay, so thanks for tuning into the video. Let me know if you have questions. Make sure that you join the Zoom conference on Monday. Make sure you watch this video, get started on the homework. Let me know if you have questions. Thanks, everybody. Take it easy.